Assalamualaikum and good evening, everyone. We are from Group 1. We will present about general trends of lanthanoids. So before that, I would like to introduce ourselves. My name is Muhammad Amir Azamuddin bin Abdul Ghaffar. My metric number is 200238.
Hi, my name is Zahira Amalimiti Muhammad and my matric number is 200375.
Hello, my name is Haslia binti Muhammad and my metric number is 202527. So the content of our presentation is including introduction, electronic structure and ionization energies, atomization energies, radii, ligand field effects, standard potential and redox chemistry, and the last one is conclusions. So I will start first with the introduction. Basically, lanthanide, also called lanthanide, any of the series of 15 consecutive chemical elements in the periodic table from lanthanum to lutetium with atomic numbers 57 to 71. The significant difference between two lanthanides is only their size and ability to choose a particular size of lanthanides that allows the tuning or adjust of the properties of their compound. The lanthanides are highly electropositive metals that most commonly occur in their compounds as Ln3, where other oxidation states are stable when an empty, half-filled, or full F subshell is produced. In other words, the most stable oxidation state is 3+. It is favored the oxidation state Ln3 with a uniformity that is uncommon in periodic table, and their chemistry resembles of group 2 elements, which is, it is attained by removing outermost 2 electrons of 6s electrons and 1 electron from 4f electrons. However, 2+ and 4+ oxidation state can also be found in the solution or in solid compounds. All metals evolve hydrogen from dilute acid solutions, which is react with H+ from dilute acid to release hydrogen. A Ln3+ ion is hard-Lewis acid, which more preferred for F- or oxygen-containing ligands, and its common occurrence, which is incident with phosphate in minerals. So, the common of the oxidation state for lanthanoid is 3+, regardless of atomic number can be traced to the core-like nature of the 4f orbitals that deeply buried inside the atom and interact only weakly with the orbitals of neighboring atoms. So, the trend is crossing the row, increase in atomic numbers, and increase in occupying the 4f subshells, which make little change in chemical properties. And then moving from left to right across the period, which is increasing atomic numbers, also the radius of each lanthanide 3+ ion steadily decrease. This is referred to as lanthanide contraction. So what is lanthanide contraction? Lanthanide contraction is referred to the decrease in atomic size of the elements in which electrons fill the F subshells. Since the F subshells is not shielded, the atomic size will decrease as the nuclear charge still increase. So I proceed with the first general trend, which is electronic structures and ionization energies. So, electronic configuration of lanthanide atoms and corresponding Ln3+ ion are shown below, as in the table. All Ln3+ ions have the configuration 4Fn 6s2 except cerium, gadolinium, and lutetium, where a 5d orbital is singly occupied. So, once the two valence 6s electrons and one further electrons, which is from either the 4f or 5d orbital, have been removed, the remaining 4f electrons are held together by nucleus and do not beyond the xenon-like core, which is group 18 elements. As a rough guide, I4 is equal to I1 plus I2 plus I3, which is sum of the first three ionization energies that explain the lack of compounds of Ln4. So, the increase in nuclear attraction across the series will lead to increase in ionization energies that is modified by changes in electronic structure and total orbital angular momentum, which is L. However, trend in I3 is interrupted by three discontinuities. First, the largest occurs between europium and gadolinium, which is ionization of Au2+ must overcome high levels of spin correlation energy, whereas ionization of Gd2+ has less tightly bound d electrons. Secondly, occur between promethium and neodymium, which is referred to the quarter shell effect. The last one is occur between holmium and erbium, which is referred to the three-quarter shell effect. These both effects are less marked and occur due to changes, which is loss, no change, and gain in orbital angular momentum, which is L. That's all from me, and I will pass the presentation to the next presenter, which is Amir Zamuddin.
All right. I will continue the presentation. For atomization energies, the enthalpy of atomization is the enthalpy change that accompanies the total separation of all atoms in a chemical substance, either it's a chemical element or chemical compound. This is often represented by the symbol as you see in the slide. All bonds in the compound are broken in atomization and none are formed. So enthalpies of atomization are always positive. The variation of atomization enthalpies across latanoids is almost the mirror image of I3. Metallic bonding barely involves the core-like 4f electrons, but varies with occupancy of the 5d orbitals that overlap to form a bonding containing the localized, which is itinerant electron. When atoms condense to form the metallic state, it's energetically favorable in most cases to promote 4f electron into the 5d orbital. Such promotion is not required for gadolinium, but incurs a greater energy cost for europium. Each atom containing stable half-filled 4f shell. As a consequence, we see an increase in atomization enthalpy between europium and gadolinium, and similarly between ytterbium and also lutetium. Okay, next slide, please. The metallic radii, like in the figure shown in the slide, that is decreased smoothly from lutetium to lutetium, apart from two exceptions at europium and also ytterbium. These exceptions are due to those metals retaining their 4f7 and 4f14 electron configuration in preference to promoting an electron into the 5d orbital, which achieve stronger metallic bonding and thus a smaller metal-to-metal distance. The metallic radii thus correspond to electron configuration Xe4f and also Xe4f14, corresponding to latanoids 2 plus ion for europium and also for ytterbium, respectively. And also Xe4f and 5d1 for lutetium 3 plus for the other latanoids, where it is a number of itinerant S and D electrons formally occupying the band. All latanoids ions have the electron configuration Xe for Fn, and their radii, based on typically at full coordination, contract steadily from 116 pm to for lutetium 3 plus to 98 pm for lutetium 3 plus. The latanoid contraction has important implication for the early 4D and 5D metals, as it results in their radii and chemical being very similar despite an increase in principal quantum number. Consequently, the pair of elements like HZR and HF and NBTA in the periodic table show almost identical properties. Such a smooth decrease in ionic radius is not observed elsewhere in the periodic table. It is attributed mainly to the increase in the effective atomic number, ZF, as electrons are added to the poorly shielding for F subshell. Although detailed calculation indicate that relativistic effect also make a substantial contractive contribution. So I will pass the next presentation to Zakira.
So let's proceed with ligand field effect. As we know, the enthalpy of hydration for Ln3 plus ion is increased gradually with some fluctuation. They will have different geometry depends on their coordination number based this formula Ln OH2 and 3 plus. The aqua ions are highly labile, as expected, for large cation lacking much ligand field stabilization and nucleic acidity, with pK values ranging from 8.5 for La3 plus to 7.6 for Lu3 plus. So this is the coordination number with their molecular geometry. For standard potential and redox chemistry, as we know, Ln3 plus lanthanides is adaptively have oxidation state 3 plus. Then, in the form of coordination complex, lanthanide exists in their plus 3 oxidation state, but although particularly stable for F configuration, can also give plus 4 such as cerium, uh, terbium, or plus 2 which is europium and ytterbium ions. For Ln3 plus, the hydration enthalpy increase across the series because of decrease in ionic radius from lanthanum 3 plus to lutetium 3 plus, which counterbalance the increase in I1 plus I2 plus I3 and mirror trend in atomization energy. As a result, the standard potential of the lanthanides are very similar and close to that Mg2 plus Mg with value of E less than La3 plus La, which is plus 2.38 volt, being almost identical to E less than Lu3 plus or Lu, which is plus 2.3 volt at the other end of the series. Okay, for the Ln2, cerium and europium, most important and useful in redox properties. Europium 2 plus ion are sufficiently stable, that is, containing one electron reducing agent. For metallic, europium and ytterbium react with liquid NH3 to give blue solution that containing the solvent electron along with the europium 2 plus and ytterbium 2 plus. Aqueous ions such as Sm2 plus and ytterbium 2 plus rapidly reduce water to hydrogen. For example, samarium 2 iodide is a useful reducing agent, which is they occur oxidation reaction. Okay, for Ln4, cerium 3 plus can be oxidized to cerium 4 plus, which is a strong and useful oxidizing agent, such as in ceramic ammonium nitrate. The Pr4 and Tb4 and the oxide of this element in praseodymium oxide and terbium oxide contain mixture of Ln3 and Ln4. So let's recap what we have present just now. From the Haslia's part, she mentioned that when moving from left to right across periodic table, the radius of lanthanide 3 plus ion is decreased. She also mentioned about the lanthanide contraction, which is the result of a poor shielding effect of the 4 electron. For Azam parts, for the atomization energies, it almost mirror image of I3. Metallic radii decrease from lanthanum to lutetium, but exception for the europium and ytterbium. Ligand field effect will cause the molecule have a different geometry based on their coordination number. Lanthanides show variable oxidation state. They can also have plus 2, plus 3, and plus 4, but the most stable oxidation state is plus 3. The reason why it's also mentioned in previous presentation. So that's the end of our presentation. Thank you.